even though we might have a lot more to work with for a general polynomial than we did with something like a quadratic, being able to find the roots, the zeros, the x-intercepts, if you will, of a polynomial function is still valuable, it's still important. So that's what we're going to be looking at here, where if we can get to some of the nice techniques, we can still use them. They're not always quite as obvious. It generally takes a bit more thought to find things like factors for a cubic than it does for a quadratic, but we still have the same goal for similar reasons, and if we're lucky, can use the same processes. So we'll see an example here where we do get to use stuff that we're at least somewhat familiar with. For this example, we want to find all of the zeros for f of x equals x cubed plus 2x squared minus 4x minus 8. And with this, again, we don't have something nice like the cubic formula. There is a cubic formula, but it's not pretty, so we don't use it. We can take f of x equals all of those pieces, x cubed plus 2x squared minus 4x minus 8, and recognize that in here we have something in the vein of an x plus 2 along with terms tacked onto it, where in particular those are x squared type things. So x squared times x plus 2 would give us that. Meanwhile over here, if I pull out a negative 4, I would get another x plus 2. And factoring by grouping is a trick that falls into the same sort of category as a lot of math tricks that makes sense right after you see it, but seems like magic right before. It's just the sort of thing that, again, comes with practice for being able to understand here that you want to be able to match stuff up as best as possible. And hey, guess what? I've got x plus 2's hidden underneath both of these. So with those x plus 2's a little bit less obscured, we can then refactor this a bit more as x squared minus 4 times x plus 2, because we have one of those on each. We can undistribute it like so. Technically, when you're foiling, you're actually doing this type of thing. It's just, well, for one, you don't often erase your parenthesis, and two, you don't usually write it that way because it makes it look scarier than it needs to. At least I think it does. But from here, if we want to find our roots, our zeros, we just set that equal to 0. And then with this in mind, even though we have a bit more complicated terms, we're still going to be using the zero product principle, where I'm going to factor out that difference of squares, that x squared minus 4, into a x plus 2 and x minus 2. So technically I now have two x plus 2 terms, and the roots here would end up being x equals plus or minus 2, where if we want to be sure, if we want to know that this is actually what's going on, we could graph this. And to tie it back with what we've seen before, we could also note that with this function, with this cubic that we have, it is degree 3, and the leading coefficient is 1, so it should make sense here that this falls to the left and rises to the right, where we were able to identify our zeros. But one other thing to notice is that with this value here, that x plus 2 occurred twice. And there actually is something special that happens when a root occurs multiple times in the same factorization. It actually has a little bit of unique behavior when you have a certain amount of repeated roots, a certain amount of what's called multiplicity. And that's what we're going to see next.